Hello there and welcome back as we continue Module 6 in our class and we start working on how we're going to describe turbulence. Now remember, so far we've been talking about quantifying, we just kind of came up with like a word definition of turbulence, but we actually need some tools that are able to describe the nature and the strength of the turbulence that we are experiencing at any given time. And I'm going to tell you that there's going to be two types of tools that we're going to be used. There's going to be statistical tools. These are going to be descriptive statistics, like the mean and the variance and the standard deviation. Or there's going to be time series analysis tools like power spectra and fast Fourier transforms and so on. But let's start off by talking about the much simpler idea of describing turbulence using its statistical properties. And the technique that we're going to be using in this part of the course here is going to be what's called Reynolds decomposition. Now, depending on how closely you've read the book, you may have come across this name Reynolds before. Reynolds had a lot to do with like boundary layer meteorology. There's a Reynolds number that describes how likely the flow is to become turbulent and so on. That's not what I think of as being the most important thing. It turns out flow in the atmosphere has a high probability of being turbulent, and I'm not particularly interested in some of the types of flow that aren't very likely to become turbulent, like, you know, the flow of a plasma gas or something like that, or flow in honey or hydraulic fluid or something. And so we're not going to worry about Reynolds number itself, but Reynolds decomposition is a really interesting way of working with a time series of observations, like an observation of wind speed over a period of, what do I have here, about 6 minutes or something like that on this particular diagram here. Let's establish a notation here a little bit. Here I'm saying that this is a diagram where at any given time t, I'm going to have a wind speed u of t. Okay, that's just our notation here like this. And if I took the average of u of t over a range of values of t, from a t start to a t end or something like that, I could actually compute an average value of u, which we'll use the notation u bar. So our u bar is our average value of u over a period of time, over some window of time. And that leads us to what Reynolds was talking about when he talked about Reynolds decomposition, where at any given moment we could say that the value of u at that time t, like the left-hand side of that equation, is equal to u bar plus a value called u prime of t, which is how the instantaneous value u of t is different from the average. So let's actually zoom in on this idea here of u prime of t, where that u prime of t could be a positive number or it could be a negative number. I mean, like if I actually literally zoom in here with my magnifying glass tool here, I could pick some time t, highlighted there with that kind of green dashed line there. Well, we have a value of the mean wind in that general part of the time series, u bar, and I could see my actual observation of u at that time, u of t, is not the same thing as u bar. It is a different height above the x, it's a different height on the y-axis than u bar is. There's actually some difference between u bar and u of t. That is our u prime of t. It's the anomaly. It's how the observation at this moment is different from the average around that time. Okay, so in this case, u prime of t was a small positive number, but we could have looked at it, zoomed in on a different part of the time series, and at this time t, we have a u bar that is, the average wind around that time, and we would see that at that moment, u of t is not the same thing as u bar. In fact, there is a small difference between u bar and u of t that is u prime of t. That is our anomaly at that time, and you can see in this case it's negative. We add a negative number to u bar to get u of t. Okay, I can see how this u could be broken down into u bar and u prime. This is what Reynolds decomposition has done. It turns out to be a hugely powerful tool in any kind of fluid mechanical context. We're using it to talk about turbulence, but there's actually a zillion important things you can do with this here. Now, so far we've been doing this all using the u to mean like wind speed, but I hate that notation. I mean, I would say that we're better off remembering that u is better used as the symbol to mean our component in the west to east direction, And then we could have u of t is equal to u bar plus u prime of t. And in the same way, we could then have a v of t, where v is the south to north component of the flow. And at any given moment, v of t is equal to a v bar plus v prime of t, the wind anomaly at that time. And we could do that in the vertical direction too, where our instantaneous value of the vertical velocity, w of t, is equal to our mean vertical motion, w bar, plus our anomaly, our departure from the mean at any given moment, w prime of t. Well, once you have decomposed, to use the right vocabulary here, the flow into the mean part, the parts with bars, and the turbulent component, to use the right term from Reynolds decomposition, the turbulent component is the one with the prime on front of it, or behind it rather, you can quantify the amount of turbulence in the flow using the statistical property of the variance. Now, depending on what classes you've had, including classes with me, like if you've taken Energy 301, you might be pretty comfortable with the business of computing variance. Variance has a weird symbol. Variance is sigma squared. There's a historical reason for that. Sigma alone is going to be standard deviation. Sigma squared is variance. It turns out it's usually easier to think about variance first. So we are going to have three different measures here of the variance of the u component, the variance of, well, let's actually focus on the variance of the u here first. All three of the expressions that I have there along the right side of the slide are equivalent. Okay, you could actually show that they're all the same. It would be a very boring homework set, but you could actually sit there and show that all three of these are the same. But you could have a measure, the variance of u. Well, we have a bunch of notation here. Here we're saying that over our period of time, from like t start to t end, there are n observations during that time. How big n is would depend on how frequently you're taking an observation. Are you taking an observation once every minute? Are you taking an observation once every 10 seconds? Are you taking an observation 10 times a second? Who knows? So n will be how many observations you took during that time period, and then we just use this dummy variable k from k equals 1 to n. So like u1 is the first observation between t start and t end, all the way up to k equals n, where you could have u of n. Okay, we're just making a list here. Think of it like a spreadsheet or something like that. I mean, for that matter, we could have used that same notation to talk about the average, where we would said u bar was just the sum of all the observations from k equals 1 to n, and then dividing them up by n. I mean, that just didn't seem all that necessary. This idea of the variance is a powerful tool when describing this the turbulence in the flow. You often will see in the context of turbulence and study of turbulence and so on that they'll describe the variance as being a measure of the gustiness of the flow. How much does it tend to have like these spikes in the wind speed? Or for that matter, these minima in the wind speed. The gustiness of the flow is reflected in the variance. And for that matter, as I show over there on the right, there's actually a variance to each of the three components of the flow. There is a variance of u, which is our top equation, and there's a variance of v, the south to north component of the flow, which is our middle equation, and there's a variance of w, the vertical velocity of the flow. All of them are perfectly legitimate things that can be computed based on observations. For what it's worth, the variance of u and the variance of v and the variance of w add up to an important property. Well, then you divide by 2 or multiply by half. They add up to an important property called the turbulent kinetic energy. TKE, or turbulent kinetic energy, is the sum of those three variance components and then divided by 2. There is a quantity called, it's confusing, there's a quantity called the total kinetic energy of flow, and the total kinetic energy is the sum of just the kinetic energy of the wind, the laminar component of the flow, plus the TKE, the turbulent kinetic energy. This makes sense when you start remembering like Louis Fry Richardson's poem about the big whirls feed on the velocity of the smaller whirls feed on the velocity of the bigger whirls and so on. You are keeping the same total amount of kinetic energy, you're just transferring it from the laminar component into the turbulent component, and then down through the sizes of the different turbulent kinetic energy terms. Okay. I mentioned before, the notation is weird about variance, about it being sigma squared. Sigma is just standard deviation. So feel free to take a square root of both sides of the equation, and you've now got your measure of standard deviation. Standard deviation is often interpreted as being like the mean, the speed of an average gust. Okay, or I guess you would say like how much greater than the average speed the average gust will be. All right, makes sense. Now, a good question is, variance of U, variance of V, variance of W. Is there a relationship between these three variables? Like, are they equal to each other? Should they be, well, they're all positive because they got a square in them. Well, it turns out there's a whole mess of different empirical relationships between these, where different authors have, under different situations, been able to show, oh, well, based on observations, we see that, in general, under the conditions of relatively stable conditions over a forested canopy, this is how variance of U is related to variance of V, which is related to variance of W. Okay, well, those are all empirical, as in based on, concerned with, or verifiable based on observations and experience, rather than theory or logic or whatever. They don't derive those. That's just based on the experience of the people who studied how turbulent flow sets up over the ocean versus over a forested surface versus over an urban surface or whatever. So they're not so great. And even your textbook tends to throw those kinds of things around. For example, on box 20 of page 130 in your textbook, your book is suggesting that you figure out whatever the standard deviation of U is, and then your standard deviation of V will tend to be 3/4 of that same value, and the standard deviation of W will be about half of that same value. Well, that might be a lovely rule of thumb, but that's certainly not in general case, and I don't think that's helpful to actually like memorize or anything like that. But more generally, whatever relationships that you're going to have between the standard deviation of U and the standard deviation of V and the standard deviation of W are going to depend on a whole bunch of different environmental effects, including things like static stability and dynamic instability. So there's going to be a number of different ways that this can shake out. And in terms of the relationship as to how much turbulence is in the U component of the wind and the V component of the wind and the W component of the wind. But one decent estimate is to say that your turbulence is isotopic. Is it isotopic or isotropic? It's isotropic. I missed an R in that word. Isotropic turbulence. Meaning that there's the same amount of turbulence in all three dimensions. There's just as many eddies in the U component as there are in the V component as there are in the W component of the flow, to a good approximation. Whichever direction you go, there's just as much turbulence. This is something that's easy to see when you look at a smokestack. If the smoke is coning, if as it goes downwind with from its point source at the top of the smokestack, it spreads out equally in the horizontal directions as in the vertical direction, just sort of making a cone-shaped area of smoke headed away from the top of the smokestack, that's because there's just as many eddies transporting the pollutant horizontally as vertically, and you get this sort of cone shape heading away from the point source at the top of the smokestack. In these conditions, then, the static stability is encouraging rising motions and sinking motions. We're getting just fine numbers of rising and sinking motions on our eddies, and the pollutants are dispersed both horizontally and vertically. Now, again, I misspelled the word. It's not anisotopic turbulence. It's anisotropic turbulence. When the turbulence is anisotropic, to a good approximation, the amount of turbulence in the U component and in the V component, the horizontal components of the wind, is equal to each other. Maybe not exactly, but ish. Kind of equal to each other. But they're not, in general, going to even be close to the amount of turbulence in the vertical direction. For example, one classic example of anisotropic turbulence is where the U and the V components of the turbulence are equal. There's just as much eddies in the east-west direction as in the north-south direction, but there's no turbulence in the vertical direction. So, like, if you're looking at a smokestack, what you'll see is the phenomenon known as fanning. Fanning means there's a point source at the top of the smokestack for whatever your pollutant is, and as it is carried downwind from this point source, horizontal turbulent eddies are transporting that pollutant out over a wider and wider area, but there's no vertical turbulent eddies transporting it up and down, and so you just sort of get this triangle or fan-shaped area of pollutants fanning downstream from the top of our smokestack. So in these conditions, the static stability is preventing rising and sinking motion. There aren't any vertical eddies. There's only horizontal eddies which aren't affected by the static stability of the environment. Our pollutants then are able to transport horizontally, but are not able to transport vertically, and you get this fan fan shape as the pollutants spread out from your smokestack. Another example of an anisotropic type of turbulence would be the situation where there's not really all that much turbulence at all in the horizontal directions. So your variance or your standard deviation of u and your standard deviation of v are, in the ballpark of 0. But there is vertical turbulence. And when you do that, you're going to get looping. You're going to look at a smokestack and you see the smoke goes up and down like this. And that looping is happening because the static stability is encouraging rising and sinking motion, but there isn't a lot of horizontal eddies transporting the pollutant side to side. So they just sort of make a kind of rope-looking downward transporting downwind as the air parcels rise and sink in the plumes, and you get looping. Man, quantifying turbulence using descriptive statistics like this is not straightforward. Wait till you see what we got going on when we start trying to do it as a time series analysis. Before we get into that though, let's do some quick questions. Question 1. What are the units of the standard deviation of u? Unitless, meters, meters per second, or meters squared per second squared. Excuse me. Go ahead and make a choice from those 4 options and get a little feedback before you move on to question 2.